Welcome to This Explainer. Right now, you and I are completely surrounded by invisible forces. They're literally everywhere. Powering the device you're using right now, the lights in your room, basically the entire infrastructure of our modern world. Today, we're going to embark on a really fascinating journey to visualize the hidden mathematical rules that govern electricity and magnetism. We're going to break down exactly how these unseen forces work, relying completely on the brilliant physics laid out in our source material. So, to understand this, here's our agenda for today. We'll start with 1. The electricity-magnetism connection. Then 2. Calculating the magnetic field, followed by 3. Shaping the magnetic field. Next up is 4. Moving charges under influence, and we'll finish strong with 5. The magnetic push and pull.
All right, let's jump right into Section 1, the electricity-magnetism connection. We're kicking things off by exploring the exact moment humanity realized that electricity and magnetism were not separate forces, but actually two sides of the exact same coin. Picture this. You're holding a normal, everyday navigational compass right next to a totally ordinary, unmoving wire. Then, you suddenly flip a switch to send a current through it. Now, for centuries, people thought absolutely nothing would happen. A compass points north, reacting to the Earth's magnetic poles, right? Why on earth would a simple electrical wire change that?
Well, back in 1820, Hans Christian Ørsted actually did this, and what he discovered by total accident was a massive game changer. The needle deflected. And this twitch of a compass needle was the definitive proof that electricity actually creates magnetism. Our source notes that Ørsted even noticed that if he reversed the direction of the current, the compass needle completely reversed its direction too. Plus, cranking up the current or moving the compass closer made the needle twitch even harder. He had basically found the hidden bridge between two completely separate worlds of physics.
Here is the secret ingredient: motion. A charge just sitting perfectly still. It's kind of like a dormant seed. It only produces an electric field. But the exact second it starts moving, it blossoms, conjuring an invisible magnetic field into existence. You suddenly get this dual-layered reality just from adding velocity.
And that brings us to the golden rule, the absolute foundation of this entire explainer. Electromagnetism is literally just the study of electrons in motion. To put it super clearly, an electric current is entirely equivalent to charges, specifically electrons, moving through space. That movement is the singular spark that creates every single magnetic effect we're about to explore. Moving right along to Section 2, calculating the magnetic field. Knowing these fields exist is great, but scientists needed the mathematical toolkit to actually measure exactly how strong the field is at any given point in space. Now, instead of getting bogged down in the massive Biot-Savart Law equation, think of the magnetic field kind of like a campfire. The more wood you burn, which represents the current and the length of the wire, the hotter the fire gets. But because of that 1/r² rule, if you take just a few steps back from the fire, the heat, or in our case, the magnetic field strength, drops off dramatically.
Actually, do me a favor, hold up your right hand right now and follow along with me. This is called the right-hand palm rule, and it literally lets you feel the geometry of the math. Point your thumb like a hitchhiker to mimic the current flowing through a straight wire. Now stretch your fingers out to a point in the air you're curious about. Wherever your palm is facing, that is the exact direction the invisible magnetic field is pushing. The math literally maps straight onto your hand.
Okay, on to Section 3, shaping the magnetic field. With our right-hand toolkit ready, let's look at how simply bending a wire completely transforms the invisible magnetic field around it.
So a straight wire is really just the beginning. According to Ampere's Circuital law, altering a wire's geometry fundamentally dictates the field's strength. When we take a straight wire and bend it into a circular loop, all that field concentrates right at the center. But when we coil it repeatedly into a long tube, the field becomes incredibly intense, uniform, and perfectly contained inside. The physical shape of the matter completely dictates the shape of the invisible energy. And this is a massive deal for engineering. By wrapping a wire into a tight cylinder, what we call a solenoid, we literally synthesize an invisible bar magnet that we can turn on and off at will. The field lines inside this helix become totally uniform, exiting one end like a North Pole and entering the other like a South Pole. This is the exact mechanism running the electromagnets that securely lock your doors or power those giant heavy-lifting cranes in junkyards. Which brings us to Section 4, moving charges under influence. This is kind of the climax of our explainer. We've built these magnetic fields, but what happens when we send something crashing through them?
The resulting physical motion is incredibly mesmerizing, and it all depends entirely on the angle of entry. But here is an amazing, totally counterintuitive piece of trivia from our source. The work done by a magnetic field on any charge is always zero. It literally cannot speed the particle up or slow it down. It can only force it to change direction.
It really is all about the angle. If a charge sneaks in totally parallel to the field, it feels absolutely nothing. It just glides right through in a straight line. But if it hits exactly at 90 degrees, boom. The magnetic force traps it, acting as a centripetal force that locks it into an endless circular orbit. And if it hits at a weird oblique angle, you get this beautiful corkscrew shape, spiraling through space because it's simultaneously trying to go straight and turn in a circle.
But you know, in the real world, it's usually a bit messier. A charge is often battling both electric poles and magnetic curves at the exact same time. The electric field wants to accelerate it in a straight line, while the magnetic field is trying to bend it perpendicular to its motion. The Lorentz force is simply the grand sum of this cosmic tug-of-war. If these forces perfectly balance out to zero, the particle coasts through completely untouched.
All right, our final stretch, Section 5, the magnetic push and pull. Let's scale things way up from tiny microscopic charges to massive parallel copper wires. What happens when two of these fields overlap?
It's actually kind of paradoxical. We're so used to hearing opposites attract, right? But with parallel wires, if the currents flow in the exact same direction, they actually attract and pull towards each other. If the traffic flows in opposite directions, their magnetic fields clash, creating a repulsive force that literally pushes the heavy wires apart.
Now, look at this highly specific number. 2 × 10⁻⁷ newtons per meter. Why should we care about this? Because if two parallel wires sitting exactly 1 meter apart generate exactly this much magnetic force between them, that is the official global definition of 1 ampere of current. The whole standard for how humanity measures electricity is anchored straight to the mechanical push and pull of the magnetic force.
So as we wrap up this explainer, I really want you to remember that we are constantly surrounded by these invisible, mathematical shapes acting out their elegant rules. From a tiny compass needle twitching near a wire, all the way to massive helical spirals racing through particle accelerators, the connection between electricity and magnetism really is the invisible architecture of our reality. So the next time you flip a light switch, think about the unseen helical forces and magnetic ripples you just created. Thanks for exploring this with me.